It's disturbing my rhythm. I couldn't get in through that door.
Creatures of comfort, aren't they?
I always go in through that door.
I see. Yeah.
So no matter where you are, they have community fire.
But I kind of cleared off my plate as of yesterday.
Oh, yeah? Actually do something.
Good morning.
Right. I'm not disturbed until 3 o'clock. It is
I
definitely.
think well away from the recording equipment, so you don't appear asleep.
No, that's the current state.
And how many minutes?
I mean, they're all one's still at 10.
So what's the normal protocol?
Yeah, we sort of.
Starting fashionably late?
May as well go in, may as well too.
Usually the formal way to do it is just a formal thing. Very, very smart, socially. And I thought, okay, if this doesn't work, but it turned out to be a really good piece. You can sort of explain this is how it goes. You're not supposed to come every time, or just once a week. And you're supposed to wash yourself. And everything worked. We just did.
Oh, you were doing it. Okay. All right. Well, thank you everybody for coming to this seminar. We're very pleased to have Alastair Young here from Imperial College. He'll talk to us about hybrid block bootstrap.
Okay, thanks very much. It's great being here. I finished my lectures for the session last week, so I hope to be more engaged with the program in the coming weeks, but no doubt Imperial will find stuff for me to do. Which, so really what I'm doing in this work is revisiting a very old interest of mine, which is nonparametric bootstrapping. I think there has been a bit of a resurgence in interest in this, and in particular addressing questions like scalability of bootstrap algorithms and things like that. Okay, I should immediately acknowledge that this is joint work with Stephen Lee, former student of mine, right? A long time ago at the University of Hong Kong, and Todd Kufner, who's a more recent Imperial graduate. Okay, so basically what we're trying to do in this work is to establish some kind of general theory of optimality for a particular variant of block bootstrap distribution estimation, the moving blocks bootstrap, for a very specific problem of estimating the distribution of sample quantiles under rather mild, strong mixing assumptions. What I would like to do, I hope in the spirit of what these seminars are meant to be about, is to focus here on some of the sort of practical implications and stuff of the work, rather than on the technicalities, okay? Okay, and the key observation that I'll make right at the beginning is the discovery that, in fact, optimality in this particular problem, and I hope to have time at the end to say that although the analysis that we're doing here appears rather narrow, there are other problems which, you know, I'm currently struggling to find numerical validation of similar results for. The key observation is that actually optimality is achieved in this problem by a hybrid between what's known as the subsampling bootstrap and the moving block bootstrap. Now I'll explain try to define these things in a minute. But the key observation then is actually that when we're doing the inference in this problem based on non-parametric bootstrapping, resampling of blocks, the discovery is that the bootstrap samples that we should use to perform the inference should actually be smaller, right, than the original data sample, right? So some kind of descaling is actually optimal. You optimally do things by naturally doing your bootstrap computations on resampled data sets of smaller magnitude than the actual data sample that we have before us, okay? I'll make that precise. Okay, so here's the problem, okay? So I'm going to assume that our data sample x1 up to xn constitutes a sample from a state of a stationary strong mixing process with mixing coefficient alpha t satisfying for some beta curiously bigger than 5 that just comes out of the available theory. Alpha t is order t to the minus beta as t goes towards infinity. Okay, as a comment, such assumption is pretty mild. The examples that I'm going to give, you've actually got exponential decay of those mixing coefficients alpha t. F is the underlying common distribution, marginal distribution of the x's, and Fn is the empirical distribution function of the observed data sample. Okay, and then for p between 0 and 1, xi p is just the pth quantile of the underlying distribution f, and xi n hat is the corresponding quantile of the empirical distribution. Okay, and the inference problem is you give me an x fixed, then what I want to do is I want to estimate this quantity, get this to work, gn of x is the probability under sampling from whatever the unknown underlying stationary process is, root n xi n hat minus xi p is less than or equal to x. Okay, so a very simple distribution estimation problem, right? Okay, well, the basic idea of block bootstrap methods, I'm sure you're familiar with. The idea is that of taking the original data sample, x1 up to xn, and in the variant of block bootstrap that I'm going to be considering exclusively here, what we do is we break that sample up into a set of overlapping blocks of size L. Okay, so BI denotes the block of successive L successive observations drawn from the original data sample starting at xi, so xi, xi plus 1, and so on. So together, those overlapping blocks are n minus L plus 1 in number. Okay, okay. But the point is that they overlap. Okay, and then I'll let B1 star up to B star be simply a random sample drawn with replacement from that collection of blocks. Okay, and the basic simple idea behind block bootstrap methods is that these B resampled blocks of observations are spliced or pasted together to form a bootstrap data series. Okay, and of particular interest to us is the case where B is equal to 1. That's what we mean by the subsampling method, the Whitish-Romano subsampling method. Okay, so your inference is based on drawing single blocks of a suitable length L from the original data series x1 up to xn. The moving blocks bootstrap, as I called it, would take effectively B to be n over L. It's the largest integer less than or equal to n over L. So the moving block bootstrap, if you want to think of it in those terms, it works by splicing together the randomly chosen blocks from the original data series to give you a bootstrap sample that's of length n, okay, or close to n, right? And the key observation, the key remark, again, just to stress the point, is you actually find that doing something in between these two extremes turns out to be optimal in the sense of the convergence rate of our estimator of that inferential quantity that distribution function value that's of interest to us. Okay, so what we're saying is take the original data sample, break it up into a series of blocks of length, each of length L, and we'll talk about what the optimal way of fixing that L is, and then you sample some number of them B, and then you splice those together to form your bootstrap sample series, with the bootstrap sample being, as we'll argue, optimally smaller than the original data series.
Do you keep them in the same order when you subsample? So if I subsample B blocks, are the B blocks in the same order as they were in the original time series?
No, I mean, the sampling process is I just take my data series and I construct from it this collection of n minus L plus 1 blocks, and then I randomly choose those with replacement. If we denote the selected thing B1 star up to BB star, then I splice those together. The first portion of the bootstrap sample is whatever B1 star is, then B2 star. So these blocks are not necessarily occurring in the order in which they appeared in the original data sample. Okay. So that's the key thing, is actually splicing together some number of blocks chosen from the data series, bigger than 1 but smaller than giving you a bootstrap series of length n is optimal. Okay. Now, some remarks. I should, of course, acknowledge at the beginning that the bootstrap literature is full of discussion of variants of block bootstrap methods. So you can have non-overlapping blocks, and you can propose very many different variants to do quite basic things that I'm ignoring here, like to ensure that the bootstrap data series are actually stationary, right? We're assuming that the data sample x1 up to xn that we're working with is a sample from some stationary process. But if you think about it, the process that we just discussed in detail of how you draw your bootstrap sample means that the bootstrap samples are not actually stationary. I mean, crudely put, the observations in the original data series at the beginning and the end, right, of different kind of chances of being in the bootstrap series and so on. So there'll be lots of variants which we could argue it might be inferentially more appropriate to be considering, which we could propose or adapt the analysis to, but I'm not going to do that here, okay? The key observation to make about subsampling is that in the literature, that has generally been presented or proposed as a device to ensure consistency of the bootstrap estimator. Okay, that's actually not relevant here. It turns out that the subsampling, so taking in the description that I've given B equal to 1, so your bootstrap series just consists of a single selected block of observations from the original data series, that actually gives you consistency. Okay, so it is important to acknowledge that subsampling, like the M out of N bootstrap that has been much discussed for the more conventional IID sampling situation, these are generally ideas that have been put forward basically to patch up the fact that the bootstrap based on sampling data sets of the same size n as the original data sample don't necessarily work. Okay, the moving blocks bootstrap generates bootstrap series that are only going to reproduce the original dependence structure of the unknown underlying data generating process asymptotically. But of course, in the subsampling method, perhaps the justification for having interest in that is that the original dependence structure present in the data sample is exactly retained, because we're only sampling a single subsample. Right? You're not splicing together independently chosen blocks and stuff. Okay, so these are some remarks to make. Okay, right. Okay, so formal details of how all this works. Okay, so L, remember, is the block length. B is the number of blocks that we're going to splice, and for X fixed in R, J1 up to JB are just indices. Okay, chosen from the set 1 up to n minus L plus 1 indicating which set of B blocks of the original observation sample we're splicing together to generate the Bootstrap data sample. Okay, UI of x is just the proportion of the original observations xt in the ith block, if you like, that are less than or equal to x. Okay, and UI star of x is just a proportion of observations in the ith block that is randomly chosen from the original data sample that are less than or equal to x. Then fn twiddles is just the average over the blocks that we can choose, okay, the blocks of this quantity ui of x, and fn star is just the average of ui star over the b randomly chosen blocks in this block bootstrap scheme. Okay, for our p in 0 to 1, I'll define xi n twiddles to be the pth quantile of this object. Okay, now I don't want to dwell on this, but the important point is, as we'll see, that that is the appropriate centering constant to use when I define what my hybrid block bootstrap estimator of this distribution function gn of x is. Okay, and then for completeness, xin star is just the pth quantile of this thing. Okay. Okay, right, so we have to make some assumptions. We're going to assume that the underlying f, remember that's the common marginal distribution of the x's under our assumption of stationarity as a density that's well defined, as our neighborhood of the true pth population quantile, and things are bounded away from 0 and infinity. Right, then there is the definition. Okay, so our block bootstrap estimator of gn of x, which we defined a while ago, which was the distribution function of some scaled and centered version of the sample quantile, is gn hat of x, which is just the probability under the block bootstrap scheme that I've described that this thing, okay, is less than or equal to rx. Right? Okay, and I don't want to bore you with the technicalities, as I said, because I'd like to move on and get some feedback or thoughts on some of the pressing computational things that arise, but just sketch for you very briefly some of the theory. The case where beta, remember I was assuming that the mixing coefficients were decaying at rate t to the minus beta, so if you crudely shove beta into infinity, you're thinking about something that exponential mixing. Then the conclusion of the analysis is that the error rate, so the difference between true quantity, okay, unknown quantity, and our estimator of it, the difference between those is optimized by setting the block length, L, right, and the number of blocks, B, that we resample in our block bootstrap scheme, both to be proportional to n to the 1/3, okay? Which means, you know, L times B is of order n to the 2/3, okay? Instead of the moving blocks bootstrap scheme, where the bootstrap series are going to be of length n, okay? And the difference is explicitly between gn hat and gn is big OP of n to the minus a third plus delta for any arbitrary small delta bigger than 0, right? Okay, so that's the conclusion. What about the competitors, if you like, the two extreme ends of this spectrum that we provide ourselves by allowing B to be whatever we like. For the moving blocks bootstrap, essentially the optimal convergence rate is n to the minus a quarter, and is achieved for block length L, anything between n to the quarter and n to the half, and B, of course, chosen, the number of blocks B are chosen to give our series to be of length n, right? For subsampling, which remember corresponds to fixing B to be equal to 1, the optimal error rate is of order n to the minus a quarter, and is achieved by a block length L, which is proportional to the square root of n, right? For the non-exponential mixing rate, or polynomial mixing rate, the case where the mixing coefficients are decaying like t minus beta, for beta between 5 and infinity, right? The convergence rate of the Bootstrap estimator is optimized by these things, right, which are kind of completely non-intuitive kind of thing. But the important point is that you see that the optimal L and B have got the same order of magnitude, and unfortunately they depend on the beta, the mixing rate, and of course in practice that's not going to be known to us, okay? And just to give you some ugly formula, in the cases for beta between 5 and something, right, and beta between something and infinity, the optimal rates are these things as powers of n, again for an arbitrary delta bigger than 0, right? Now that's not necessarily the most helpful thing that we have. What we can see is that if we take the block length, L, and the number of blocks B that we splice together in the creation of these series, both be proportional to n to the third, then the Bootstrap distribution estimator has a convergence rate, and that for any beta bigger than 5. Okay. Again, the optimal convergence rate is going to depend on beta, but of course, setting L and B in this way is not setting L and B with knowledge of the unknown beta. Right? Okay. In the case of the moving blocks Bootstrap, it turns out that in this case the optimal L is of order cube root of n, so that necessarily therefore the number of blocks that we splice together is of order n to the 2/3, and the convergence rate, for what it's worth, of the corresponding moving blocks Bootstrap distribution estimator Gn hat is given by this, and compare that with that, right, and see if you can make sense of.
So I had a question about the previous slide. You said that at the very top, the previous slide, that you're assuming that L is order B.
Yeah.
Is that the assumption under which this is optimal? Is it possible that there's a better rate if they're not the same?
Yeah, I guess you're right. I mean, the theory is worked out making some assumption that L is of order B.
Okay. Because that's exactly the opposite of what MBB is doing, right?
Yeah. So I'm not sort of claiming that this is the sort of strongest form of assumptions and things that we can make. Yeah. So here we would be having L in the same order. Okay, so the important point is that again you can convince yourself by comparing these with these that the convergence rate for the moving blocks thing, right, is actually markedly slower than what we would get by our hybrid scheme, in which we just decide to take L and B both to be proportional to the cube root of n. Okay, so that's all I really want to say about the theory. So let's look at a very simple example. Okay, so what I'm going to suppose is that the observations of my data sample x1 up to xn have actually been generated from an ARMA 1-1 model of the kind that is shown there, with the epsilons actually being independent standard normals. Of course, in the inferential procedure, the blocks Bootstrap procedure, we're making no such assumption, right? We're just treating this as a sample from some unknown underlying distribution. This is a case actually where the strong mixing assumptions that we're making are satisfied. We've actually got an exponential rate, or in the way that we've phrased things in what I presented, beta is infinity. Okay, and basically I'm going to show you some simulation results here, in which, just to be very particular about it, I suppose that things are initialized according to the marginal distribution. So if that's the data generating process, the marginal distribution, right, of any x is actually a normal distribution with this funny variance, and I suppose that we set epsilon 0 to be a standard normal thing. Okay. Then Luke, in some rather limited empirical analysis that I'll give, the median, so p quantile, finding the quantile is a half, so of course the the true xip is equal to 0, since the marginal distribution is normal, means 0. And then what we can do is we can determine either analytically or just by fixing, running a little simulation program and running it for a long time, that for a sample size n is equal to 200, okay, then the quantity, this distribution function value at x is equal to 1 that I'm interested in estimating basically is, it's about 0.7, okay, so I just stress that not because that number is particularly important, but to say two things. I suppose we're looking here at the case where we're looking at the median, where you might expect things are going to be nice there, so in the middle of the distribution, and we're looking at inference for probability that's not particularly extreme. Okay, but then what we'll do is for a range of values of b and l by simulation, just estimate the mean square error of the hybrid block bootstrap estimator of that quantity, and the numbers that lead to the heat map, I'm going to show on the next slide, are each based on, so we're doing 20,000 replications for any given specified B and L, and each block bootstrap estimator is constructed using 20,000 block bootstrap samples. Okay, in the subsampling case, each such block bootstrap sample is determined by just sampling B equal to 1 block, but in general it will be sampling B blocks of size L. Okay, and there's the thing, it's not necessarily brilliantly clear, but what you observe, okay, so B equal to 1, right, and then L, so that is subsampling, right? And what you see is, okay, this zone here, and you've got the smallest mean squared error for values of B, which are of the order like 7, and L block length between about 6 and 10. It's giving substantially lower mean squared error in estimation than either of the two extremes, the subsampling or moving blocks. Okay. In fact, for what it's worth, to be concrete about the comparisons, for our hybrid scheme, you find that the optimal B and L are 6 and 8 respectively. Remember, n is equal to 200 here, so we're saying that optimally we do our inference by drawing bootstrap samples of size 48, right, from the data sample of size 200. Okay, and the mean squared error to 5 decimal places is shown, and by comparison, the optimal implementation of the moving blocks bootstrap, which requires the product BL to be close to n, here equal to 200, that's achieved by splicing together 33 blocks, each of length 6, and the mean squared error is about quite 50% higher than you get by setting B and L, allowing yourself the luxury of setting them to be anything and choosing them optimally. And the subsampling method, which remember corresponds to B is equal to 1, the optimal, the minimum mean squared error is somewhat larger still and is achieved with the block length equal to 14. So that would be the scheme in which you're doing this estimation by repeatedly sampling a single block, B equal to 1, but of length 14 in the definition of the bootstrap estimator. And I think I could have chosen to give other examples where maybe the comparisons between the minimum mean squared errors are more striking, but I think it would be, I would argue that such a reduction in mean squared error is a worthwhile thing to have targeted, right? Change n, I've increased n here, 200, 500, 1,000, and 2,000, and asked what are the optimal B and L for estimating Gn of 1 for different sample sizes. That true value was about 0.7. In the case n is equal to 200, it's not actually terribly different for these larger values of n shown here. The optimal B and L that we get from the hybrid scheme, still under this ARMA model, are as shown here. So for example, for n is equal to 1,000, the optimal thing to do is to take B equal to 10, L is equal to 14. So that corresponds to drawing bootstrap data sets from the original data sample of size 40 rather than 1000, which is the length of the original data series. And if you're able to fit a regression, right, to these minimized mean squared errors here as a function of n, you'll find that it fits very nicely, the theory that the mean squared error should be decreasing as n increases at rate of n to the minus 2/3 or something, right? Okay, now are we typically going to be interested so specifically in the inference that I described, which is for my fixed x, right, which I set to be equal to 1, remember, in the analysis that we just shown. Are we actually interested in that gn of x? No, probably not. We're probably going to be wanting to use the estimate of that distribution function gn to construct a confidence interval for the population quantile or whatever. And I wanted to sketch that, in fact, the theory that I give the highlights of is directly relevant to analysis of coverage error of rather crude confidence sets that we could construct by this block bootstrap scheme. So I'm going to define a quantity delta, which will depend on the sample size, the number of blocks, and the block length L by this. So delta is our estimate minus this normal asymptotic thing, right? Then, in fact, what our results do is to establish the asymptotic order of this quantity delta, and we derive, and I stated the rather ugly formula that describe the optimal orders of B and L, okay, that minimize that, right? Now, there's no claim here that this would be at all a sensible thing to do, but one could, okay, use my distribution function estimator. So gn hat is the quantity that we construct by the hybrid resampling scheme. We could use that to rather crudely construct a level alpha, nominal level alpha, lower confidence limit for xip, so that's the pth quantile, right, of the underlying marginal distribution of the x's under our stationary process. It can be defined as there, okay? And it's not difficult to see that, in fact, the probability under resampling that this thing, this limit, is smaller than or equal to the true but unknown xip is the nominal desired level alpha up to a term that we can describe in terms of a delta, so that choosing for our given n, b and l, to minimize the order of that quantity delta is also minimizing the order of the coverage error of such a crude confidence interval or confidence limit for the population quantile. And let me show an illustration of that, because I think it's quite interesting that you don't get the stark picture as we got when we were just looking at this estimation of GN1 in the ARMA model. Let's suppose YT is a sample from an ARMA 2-3 process described here, sort of fixed particular values of the coefficients, but let the observed process, as it were, XT, be the square, okay, of YT, so it's a non-linear thing. Bored with what do I need to do? That's gone, right. Bored by your seminar, yes. Is this deliberate? Again, for such a process, which is a little bit more interesting simply than the ARMA 1-1 process that we looked at before, you've again got an exponential mixing rate in the paper. We look at, or attempt to, again, it might be interesting to discuss this, try and empirically look at a process where there is a polynomial, not exponential mixing rate, but then you get into issues about approximating things numerically and stuff. Okay. Again, I'm going to in my series of 20,000 replications, I'm going to initialize the generation of the data series of length n is equal to 200, which I'm going to do the bootstrapping on from the marginal distributions, right? And I'm looking at construction of lower nominal 90% confidence limits, again for the population median, which of course is not equal to 0, right? Because the observed process is the square of the RMA process. Coverage error examined by a similar kind of numerical thing as before, namely do 20,000 replications, generate 20,000 data series from such a process, and for each look at different hybrid block bootstrap samples, and in the analysis use 20,000. I mean, this is overkill, right? 20,000 block bootstrap samples of the appropriate size, the appropriate length for each of these replications. And there's a heat map that shows the coverage error. Okay, and you can see that if you set B and L to be very, very small, you get huge under coverage, right? But for the most part, you actually got, it's this color, right? Most of the time. So you actually have very, very slight under coverage across a wide range, right, of choices of the number of blocks B that we splice together and their length. And then just in in the rather finite simulation we've done in just 1 or 2 choices, you've got slight over coverage. Right? Okay, so I mean, I don't know what to make of that, but it's kind of interesting, maybe from the perspective of coverage error, the choice, right, of B and L that we need to make is going to be less crucial than it was in the case of estimation of the distribution function itself. Okay. Okay. Now, of course, this is all very well, right? This is where things get a little bit fanciful. Okay. This is all very well. So we've made the basic theoretical observation that in this problem, and I hope to have time at the end to remark that there are other problems which the similar kind of theory should apply to. We're making the observation that it's a good idea from an inferential perspective to base our Bootstrap algorithm on the generation of Bootstrap data series of B blocks of length L, with the product BL being smaller, potentially significantly smaller than the observed data sample series. Okay, but how do we choose B and L? Okay, so here is an attempt, right, to describe a procedure which is very much under development, which we could use to try and determine in practice, given only the observed data series, what B and L we are going to choose, right? So effectively, what we're wanting to do, remember, the optimal B and L that we're going to be looking for are proportional to n to the 1/3, where n was the size of the original data sample. So really what we're doing is we would like to know what are the coefficients C1 and C2, so that setting B and L as there is going to minimize the estimation error, or in some rather natural extension, the coverage error, right, of our confidence limit. So the natural thing to do is to consider using a block bootstrap scheme, right, to construct an estimator of that estimation error, okay? And such a block bootstrap estimator of the error would be based on the idea of resampling blocks of size m from the original data sample, okay? And effectively comparing the estimator that we get for such a resampled block of size m with the estimator that we get from the full original data sample of size n with such a prescription of B and L. Okay, I hope that's not too terse. Okay, so specifically, what I'm going to do is let capital M be some subsample size. Formally, we would require it to be order little of n, but tending towards infinity with n. And let g m hat j of x be constructed exactly analogously to the way we constructed g m hat, but doing that okay, not on the complete original data sample, but on the jth block of capital M consecutive observations drawn from the block. Okay? And obviously, if I fix at M the number of such blocks that I could be considering is n minus m plus 1 in number. Okay? And then I'll define error quantity C1, C2. So this is just averaging over these n minus n plus 1 blocks some measure of the difference between the estimator constructed from that block of observation, okay, with C1 and C2 fixed. And so just to be fixed in the evaluation of that quantity, the block number is C1 m to the third, and the number of each block is of length L, which is C2 m to the third, and this is the estimator calculated on the full data sample size n with the coefficients C1 and C2 so fixed. Okay, that we could do for any fixed row. I don't know why I'm afraid of things in general terms. Okay, then it's not difficult to show that error estimator, right, that I have defined, speak about some of the computational considerations that would go into evaluation of that, that's minimized asymptotically at the C1, C2 that minimizes the corresponding estimation error of the block bootstrap estimator. Okay? So that's just asymptotically, we're justified in choice of C1 and C2 to minimize that error quantity that I have described to you. Of course, to construct that, we've got to choose the block length L, the block length, the number, sorry, of blocks M that we're going to be constructing the error estimate from. Okay. Okay. As described, that error estimate is going to be constructed by considering all n minus m plus 1 subsamples of m consecutive sets of observations drawn from the original data sample of size n, and therefore you can imagine it's going to be computationally rather expensive. Okay, but it turns out actually that the argument supporting the choice of these coefficients C1 and C2 by minimizing that error estimate actually only requires that the number of subsamples, okay, should grow with the sample size. Okay, in practice and in the two cases that I'm going to contrived cases that I'm about to show you, it's quite reasonable to evaluate that error measure, not using the full set of what was it, n minus m plus 1 blocks, right? But just using a smaller set of subsamples, such as 20, and then spacing those out equally across the original data series of size n. Okay, and that's indeed what we did. Okay, so you can see how contrived some of this. Suppose I set the sample size n to be equal to 512. That is 8 cubed. Okay, right? And then for that, you can work it out. And this is again for the nonlinear, so the square of the ARMA 2-3 process. You can check analytically or by simulation that the quantity Gn at x is equal to 1 is again not extreme, but it's about 0.8. Okay. And what I'm going to do is I'm going to restrict attention to candidate values for these coefficients C1, C2 in this set. So consider just having C1 and C2 taking the values of half, 3/4 and things. So that, of course, you can quickly do the arithmetic, right? N is 512, so n cubed, n to the third rather is 8. So C1 times n to the third and so on means that effectively what I'm restricting myself to doing is to adaptively choosing from the given data sample by minimization of this block bootstrap estimate of the error, I'm restricting to an adaptive choice of the number of blocks B and their length L from this set here. Okay. And what the table I'm going to show in the next slide is obtained by looking at the mean squared error in estimation of this quantity over 2,500 replications for each combination of C1 and C2. Maybe I should skip to that. And there is, right, the result. Okay, so, each setting of C1 and C2 corresponds to a setting B and L, and the mean squared errors that you get over by simulation over 2,500 replications are as shown there. So you see, some, you know, if we take B and L both to be kind of big, right, you get much larger mean squared errors in this context than we do if we take C1 and C2 to be small, corresponding to smaller values of B and L than these other ones. Okay. And what we found, you know, using this adaptive procedure of choosing for any given data sample the C1 and C2 in the set that I'm allowing us to consider, finding the value of C1 and C2 that minimizes the error measure. Sorry, using the computational shortcut of just using 20 subsamples in the construction of that quantity, and fixing in the procedure for construction of that error measure m to be equal to 64. 64 is 4 cubed, right? So m to the third is 4. So again, C1 times 4, C1 or C2 times that value 4 gives us a nice integer value in each case. I'm just fudging things so that I don't have to worry with having to take the nearest integers and stuff. And the point that's highlighted in blue is that over these 2,500 replications, the mean squared error that we obtain, okay, using the method that was suggested of minimizing this error measure on each data sample, that yields overall a mean squared error of 0.20189, which of course, if you compare with the mean squared errors in this table that we get over the 2,500 replications by just fixing always B and L, you can see that it's not that great. Okay, you certainly do better than you would have done, okay, if you had just naively fixed C1 and C2 to be larger, so that is to take larger values of B and L, but you do significantly worse, right, than you would do by, say, fixing C1 to be 0.75 and C2 to be 0.5, which corresponds to B equal to 6 and 4 and 6 and 8. Right? So that's, I think, a proof of concept. It might conceivably give you something worthwhile, but it's going to be far from an optimal way of choosing the number of blocks B and their length L. Let's jack up the sample size n to 1,728, right, which again is a cube, a nice number. And now the still fixing x is equal to 1, the gn of x is still about 0.8, so it's not a particularly extreme value. And take in the procedure for construction of the error measure, which we minimize with respect to C1 and C2, take m is equal to 512. So again, it means that we're adaptively choosing our block number, B, and the block length from this set of values. Again, using the idea of just taking in the construction of the error measure just 20 sort of equally spaced subsamples of that length 512 from the original data series of length 1700. Okay, and now the adaptively chosen estimator has a mean squared error over 2,500 replications, which is 0.3066. So remember that figure, and if you compare that, right, with what we see in this table, which again is showing the mean squared errors that we would see if we were just to fix B, and fix L, you see that in fact it's quite competitive, right? You're getting almost over the set of choices, C1 and C2, a mean squared error from the adaptive procedure that is pretty close to the best that we could get, okay, were we to have fixed C1 and C2 to that value throughout, okay? So I hope these figures convince you that this idea of using a further level of block bootstrapping to construct some error measure as a means of choosing the actual block number B and block length L that we're going to use in this hybrid scheme has got some sort of mileage in it. You can imagine there's all kinds of things that we could do, right? I mean, maybe for a given replication, the thing to do is to fit some surface, right, to the as a function of C1 and C2 rather than just restricting, choosing which value in a finite set of C1 and C2 gives us the smallest error measure. So there's fancy kind of things that one presumably can do, but there's no claim that the described scheme is necessarily asymptotically going to give us the optimal thing, but figures, at least in this case, at least this table, albeit for a large sample size n, at least are suggestive that if n is big enough, such a scheme might not be so bad. Okay, so that's about what I was wanting to do. So in conclusion, right, this is the key point: is that a bootstrap inference, the idea of doing an inference by resampling in some way from your original data sample, that bootstrap inference is generally based on the notion of mimicking the sampling variability that gave rise to that, the actual data sample, using resampled data sets of the same size, right, as you have in the original data sample. So even recent discussions of ideas of scalability of bootstrap methods and stuff, I'm thinking here of things like the bag of little bootstraps, although they're based on very neat ideas, that procedure in particular of taking my potentially very large original data sample of size n and sort of dividing it into sections, right? Within each bit, okay, of the data sample, you're still doing the calculations to estimate the sampling distribution of a statistic for samples of size n, right? So it's still sort of working with the notion that it's best to be working with resampled data sets of the same size n as in the original data sample. But what we've seen here is that basing a bootstrap calculation on smaller resampled data series is actually best. And just to remind you that, you know, this idea of basing a bootstrap calculation on resampled data sets of smaller size than the original data sample hasn't, I think, until now been seen as a device to optimize the bootstrap inference, but rather as a device which we need to wheel in to ensure basic consistency of the bootstrap estimator. So what we're doing here in this work, I think, is to establish that, I say in key context, in some contexts which presumably are both inferentially and conceptually important, there are theoretical and practical reductions, worthwhile reductions in error that can be achieved by deliberately electing to use a smaller resample size in the bootstrap calculation. And so I propose to you the idea that this discovery might have some kind of implications for computational efficiency and scalability of bootstrap methodologies in the kind of dependent data settings, at least, that I've been considering here, okay? Unless you feel that this inference problem that I've looked at of estimating the sampling distribution of a sample quantile is rather narrow, the results, the theoretical results at least, extend to, for example, the use of the block bootstrap to estimate the distribution of a kernel density estimator if the underlying process is a stationary strong mixing process. So how does the kernel density estimator behave, right, if the data sample that it's being constructed from is a sample from a stationary weakly dependent process? And the same kind of results as I've given here extend to that case. The point in that work that we've reached is actually making the rather kind of remarkable but surely wrong discovery that there, things like taking B and L to be incredibly tiny, like B equal to 2 and L is equal to 2, is very often apparently the best thing to do. But there could just be errors in the code, right, at this particular stage. Okay. And I acknowledge, hands up, that although the figures I've shown, I hope, suggest some sort of proof of concept idea, it's clear that for all of this to have much practical implication, we would need to provide some much more efficient method for practical choice of the number of blocks B and their length L that you're going to use in the bootstrap calculation. So I think that's what I wanted to say. These are the key references. Okay, thank you.
What happens when beta becomes less than 5? So I have a lot of applications in geophysics where beta bigger than 5 would kind of be unreasonable. And if you fixed your error, I mean, you were looking at the error you would get, and you wanted to minimize your computational cost, how would you pick L and B? So you allowed for a certain error, but you only had a certain computational budget. How did you then pick?
These are very good questions. I mean, the answer to the question about the beta, what happens when beta is like, ask Steve, right? I mean, I think that the presence here in what I presented of that value is just an artifact of, you know, the theory as worked out using, I don't know, the kind of distribution of things about sample quantiles that are known for these strong mixing processes. So it's quite conceivable that for those cases, you know, something analogous can be proved. I think that computational issue is something that's always kind of interested me, right? This playoff between the inferential error, right, and your computational budget, right? And in particular, plug, you know, a now very obscure paper that Stephen and I wrote a long time ago when people were very interested in iterated bootstrap things in an IID setting, okay? There, obviously, you've got two layered levels of bootstrap sampling, and we're going back here now, 20 years or something, where computational cost, even for doing that kind of thing, was a consideration. And we looked at and saw actually that, you know, there can be settings where the, if you like, Monte Carlo error, right, can be played off against the inferential error, right? So that, you know, if you say, you know, this is all kind of presupposing that we do an infinite number of bootstrap replications, right? I use 20,000, which is kind of like big for the cases. But that theory is kind of presupposing that you do an infinite bootstrap calculation on each data set that is presented to. Of course, that's not practical, right? You know, asking the question about how do these two things, the sort of intrinsic inferential error and the Monte Carlo error, how do they play off against one another? I don't think it's as clear-cut as people have perhaps sort of thought, right? So if you've got a constrained computational budget, right, it might actually be a good thing, right? Because it might be that because you fix the total computation in the bootstrap calculation, you actually can improve the bootstrap thing than you would achieve if you had no computational constraint.
Well, for instance, I mean, I think what will happen is you won't pick L and B to be the same order, as someone said before.
Yeah.
And if I maybe have a random field, you get a lot more boundary effects. Picking a small patch is a lot more problematic. What do you think is going to change?
I don't know. It's a very interesting question. Yeah, I mean, I suppose for the kind of context here, I think that perhaps because you're looking at these simple RMI type models and things, perhaps those sort of considerations that, as I indicated, lead to saying, you know, no one in the right mind would do moving blocks bootstrap, right? Because you're constructing data series that are non-stationary and all that. You use these circular things of wrapping around and fancy variants that, and maybe we're kind of admitting here that we're looking at things where those kind of effects are not important and therefore justified in focusing in on this very plain vanilla variant. I think in more realistic context, probably those issues would become much stronger.
So when you're looking at the error in these distribution function approximations, is those errors uniform with X or for a specific X?
We're fixing X, right? So you're fixing an X, right?
So the error could depend on X.
So the error could depend on X, yes.
Optimal choice of B and L could depend on X.
Yeah. And I could say, you know, one worries about things like, you know, what happens if we put X is equal to 1, right? Then you find that the true quantity is 0.8. Well, that sounds okay, right? Because it's not too extreme. But, you know, playing around by looking at other things, the gut feeling is that things are not depending on X very much, right? I could change, I'm looking at GM, some extreme thing. You get similar heat maps and things coming up, but there's no theoretical support for that. You're right, the errors can depend on what the fixed X is.
In the last part, if someone told you what beta was, could you use that to get an even better estimate? Or put another way, if you would you get some mileage maybe from trying to estimate beta first?
Potentially, yeah. I don't know. I mean, in the paper we kind of look at some things. So the suggestion here is that in the case where the optimal B and L depend on beta, where you don't know it. So how much worse do you do by just taking that to be of order the cube root of n? And I think the answer is not very much. But that doesn't mean to say that you might not be advised to use that. Estimate beta and then use the optimal things for that, maybe in an empirical adaptive kind of scheme.
I get the impression, and I might just have misunderstood something, but the basic intuition here is we're going to try to keep the local dependency in each of the blocks, right? Are there scenarios, especially when you're trying to estimate something like a distribution function, where that dependence is actually what is hurting the estimate? And somehow it would be a better idea to do a completely different sort of bootstrap, where you sort of purposely chose pointers sort of far apart, just to kill the dependence between them. Or does that make no sense at all?
Quite possibly, right? I mean, so the idea, I suppose, is that if I choose a block, right, then that block really does represent, right, a set of observations drawn from the underlying process and therefore reflects in some sense the dependency, right? Where we screw things up is by splicing together independent things so that at the ends of blocks we're not capturing the dependence. I suppose, you know, generally if you knew more about the dependent structure, then presumably there's something much more clever than you can do than just block resampling.
Well, I feel like if it was positive dependence, you'd want to do the opposite somehow. If you have like a positively dependent time series, so every xn is very, very highly positively correlated to xn minus 1. Yeah. And I kind of feel that if you take a bootstrap sample of that and a block, then you get a very poor estimate of anything, right, about the true marginal distribution, because you don't really observe anything like the full range of a marginal distribution when you're looking at such a small dependent portion.
Okay, provoking. Yeah, thank you.
Any other questions? Thank Alastair again.